there are 3 oscillators in this system that are specifically meant to produce audio pitches, and there are a few more that are meant to produce low frequency signals that you basically use to modulate. But you can do modulations at low frequencies. You can also do modulations at audio rate frequencies. So for me, I don't really make a lot of distinction between LFOs and audio oscillators, except that the audio oscillators have this, because they're analog and they're slightly sensitive to environmental things like temperature and humidity. They have this extra special circuitry to stabilize their pitch for temperature, etc., 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 which are not on the modulation oscillators, although they can also go into the pitch range. That means that if you want to have exact tunings, you need to use the audio oscillators. The others you can also tune exactly, but if the temperature changes or the humidity changes, they may drift a bit. So there are, from the 3, there are 2 of the same type, and there's 1 that is of a different type. And these are really very different kind of oscillators. The first oscillator that I will talk about is of my own design, and with this oscillator, actually it's the oscillator that also started me to build these systems, because the idea is already very old. I think I came up with that in the second half of the 80s with the algorithm to do this, which at first I used on a computer as a digital algorithm to calculate samples for an Akai S900 sampler that I bought in 1986, and together with a little 16-bit Atari computer, I was able to sort of calculate sounds and dump them to the sampler over MIDI sample dump, which means that it took, for 1 second of sound, I had the Atari calculate one night, and then it took 20 minutes to sort of transfer that 1 second of sound over MIDI into the sampler, but then it was there. At that time that was spectacular. These days, of course, it's completely old-fashioned. But some 15 years ago, some 15 years ago now, 14 to be exact, I tried to implement the algorithm on a DSP, and I ran a bit into trouble, and it puzzled me because I very clearly remembered that I got it perfect in the second half of the 80s, and the DSP didn't really respond that well, and the difference was because it is a method that uses feedback to produce harmonic series. And originally I used proper recursion, meaning that I would calculate the recursion within 1 sample, up to maybe 100 or 200 times. And I wasn't able to do that on DSPs. And with DSPs I always had to work with the Z-1 delayed sample, and that sort of introduced phase shifts over time that sort of destroyed the algorithm a bit. And because I was sort of puzzling about what to do, I just decided by chance, I just had this idea, why not set it up on an analog breadboard and see what the analog, if an analog version actually does something. So I did, and it immediately worked perfectly. So, and I thought, hey, that's interesting. And so I actually built a prototype of it. And some other people said, hey, this is a really interesting kind of oscillator. And then I thought, okay. And basically that developed into this system. That's how these things, you don't decide to become a synthesizer designer. It happens to you, really. Well, it happened to me. If you decide to become a synthesizer designer, you have to see your psychiatrist, actually. What is the difference between a traditional oscillator, a traditional so-called sawtooth, sine, triangle wave, square wave oscillator, is that this oscillator basically starts with a sine wave and a cosine wave, and then by means of a mathematical calculation, it produces the harmonic series. And so basically the property of this oscillator is that all these three parameters that you find in a sound, you can already control on the oscillator. First of all, I can control the level. And by default, you hear a sine wave. Then I have a little knob here, and I can add harmonics. Which is a harmonic series that contains all the harmonics and eventually builds up to the spectrum of a sawtooth sound. I have another knob here that basically create a harmonic series that only has the odd harmonics, which is the harmonic series of a square wave or a triangle wave. And the interesting thing is that I can combine these together. You hear an effect that is known as pulse width modulation of a pulse wave, where you modulate the pulse width. And because that is what all the traditional oscillators have, I thought, okay, so basically this is a good replacement for a traditional oscillator, but it has one thing extra which is of interest, and that is now you also have control over the basic brightness of the sound, because you can make it very bright or much less bright. And why would that be of interest? Well, very simple. Most probably the sounds that you generate will be in a combination with sounds from other sources. That might be acoustic instruments, that might be vocals, etc. And one of the things that you have with, if you work with acoustic sounds, is that basically the area above 5 kilohertz is fully reserved for the acoustic sounds and for the vocals, because there is something in the mix they call the air in the mix, the subtleties in the vocals, specific things in the acoustic instruments. If you have an electronic sound that produces harmonics in that range, it will mask away those subtleties in the acoustic sound, and that way it can sort of destroy those sounds. So many times if you would like to make a mix and you work with different instruments, electronic music instruments and acoustic instruments and vocals, you have to be able to make a very clear balance in the different parts of the spectra of these sounds. And because electronic music instruments can very easily produce a lot of energy in this really high part of the spectrum, it's not really such a bad thing to be able to already control this at the source. So, because I realized that this can be an interesting property for people that make music, I thought, well, I should really sort of build this oscillator and make it available to people, and the rest followed. So these knobs you can set by manually, but you can also modulate them. So I can take a slow modulation signal and I can apply it, for instance, first to the volume. You can already control the volume. Of course, you can also control the pitch. And But you can also control the timbre. My voltage control. Then you can So basically you have everything under voltage control. And that is basically the special feature of this oscillator. So in one sense it is a completely traditional oscillator, but you got a couple of extra features that can actually sort of be quite interesting. So the fact that you can control the brightness is a thing that can be very handy if you're doing a mix. The fact that you can also control the volume or the amplitude at the oscillator level is also interesting, because you may want to do some wave shaping later. And wave shaping basically is a means to add harmonics to a sound. But all wave shaping methods in general are very sensitive to the sound level that comes in. So if you would have an oscillator where you cannot control its output level and put it into a wave shaper, then this wave shaper will immediately go to max. So, but if you're able to sort of control the level already on the oscillator level and have it under voltage control, that might actually be a nice, interesting extra feature in your system. And in this way, basically, it is a bit different from the more traditional oscillators like they were already sort of figured out 50 years ago.
Can I ask a question? Yeah. Having the VCA to control the level on the output of the oscillator, does that have consequence for filtering as well, or not so much?
If you have a filter that has some distortion built in, then it can actually make a difference.
But with your filters?
Yes, it can make a difference.
Yeah. Okay.
Yeah. You want to hear it straight away?
I didn't want to interrupt your flow, so.
It's not a problem, because if I can demonstrate it a bit with the filter, because I have a filter here that I can add distortion in the filter. And let me see. Yeah, it's a bit, it's difficult to hear. But if I would actually even produce a bit more volume here, then this distortion that's built in the filter actually makes the filter go into a sort of chaotic range, meaning chaos as defined by chaos theory, meaning that it would sort of produce a sub-harmonic, and which is the kind of sound that you get from trombones.